Let's finish today by performing an example of the Biot-Savart Law. And in this situation, what we have is we're going to just analyze the DC current that's flowing in a conductive wire. In this case, we've got 80 amps. It's flowing along the positive y-axis from the right to the left. And we want to find the magnetic field strength and also associated direction 40 centimeters from the conductor. I'm actually going to make a small change. I'm actually going to do this from, just to keep things simple, from left to right. The current is flowing from left to right. So if we were to just draw that situation on a in the Cartesian plane, I use red to indicate current. This is going to be the z-axis. This is the x-axis. This is, of course, then the y-axis. If we've got current flowing from left to right, we've got current, an infinite line of current flowing along the y-axis here. And it has a value of 80 amps. So the question here that has been posed to us is, let's determine the magnetic field strength and the magnetic field's direction 40 centimeters from the conductor. Well, what does 40 centimeters from the conductor mean? Well, I could go 40 centimeters from the conductor in the positive x-axis, right? That's 40 centimeters away. I could go 40 centimeters away on the positive z-axis. I could go on the negative x-axis, I could go on the negative z-axis, I could go some position in space that is 40 centimeters away and doesn't lie on the z or the x-axis, that has a component that's both in z and both in x. You know, there's a variety of locations that are all 40 centimeters away. The thing that they all share in common is that as long as I'm 40 centimeters away, it doesn't matter if I'm on the z-axis, it doesn't matter if I'm on the x-axis, it doesn't matter if I've got some sort of rotation to the z and x-axis, it doesn't matter if I measure down here or up here, the magnitude's all the same, because the only thing that sets the magnitude from the Biot-Savart law is current magnitude and the radial distance of the point away. And so since radial distance of all these points is going to be 40 centimeters and it's constant current, the magnitude of the magnetic field strength at those 40 centimeter points is all going to be the same. And that calculation is pretty easy to do. It's the magnitude of the magnetic field strength is just the magnitude of the current divided by 2 pi rho. So if we've got a DC current of 80 amps, we divide that by 2 pi times 40 centimeters, or 40 times 10 to the minus 2 meters, and we get the magnitude of the magnetic field strength at any point is 31.83. Remember, units of magnetic field strength are amps per meter. So what's the direction of this? Well, in general, what we would use is we'd use the right hand rule. So imagine taking your right hand and orienting your thumb along the direction of current flow, which in this case is right to left, and then curling the fingers of your right hand around the conductor. So in this case, what we would see is that above the conductor, the magnetic field is pointing out of the screen, and into the below the conductor, the magnetic field is pointing into the screen. Right? On one side, on this side of the conductor, on the outside edge of the conductor, the magnetic field is pointing down, and on the along the negative x-axis, the magnetic field of the conductor is pointing up. And so really what that looks like is the direction of the magnetic field is constantly changing. And it is, I'm going to just extend this current element a little bit so I've got space to draw on it. Really what it is it envelops this wire as a circle. And the magnetic field is kind of looking like this. Right? There's a circle that envelops the magnetic field. And the direction is such that this circle is pointing out at the top, it's pointing in at the bottom, it's pointing straight down, if we're on a positive x-axis and it's pointing straight up if we're purely on the negative x-axis. So I think you can kind of get that. So how can we quantify that numerically? Well, what I'd like to do next with this example is let's analyze the situation at a couple points. And we've got 3 points. We've got P1, which is going to be at 40 centimeters in the x-axis. It's going to have no location on the y-axis. It's going to be, we'll just measure right here. And it's going to have no distance in the z-axis. That's all in centimeters. So we're measuring at that point right there. We're going to have P2, which is 0, 0, 40. So that's that point right there, 40 centimeters in that direction. And then we're going to have P3, which is at 28.284. 0, 28.284. So that's some point, roughly right there in space. So this is P1 here, P2, and P3. So let's look at those 3 points, and what we're going to do at each of those is apply the full Biot-Savart law, which is just the part we showed up before where we calculate the magnitude. And then we have to figure out what the direction of the magnetic field is. And we know that what the right-hand rule is saying is that the magnetic field is just tangential in the direction of phi here. Well, how do we actually calculate that? And that's what I'd like to show in these cases. So case for point 1, if we were to look at this, what we're interested in is the z-x-axis, right? We're really measuring the amplitude and radial distance in the zx plane here. So if we were to just draw that, we've got the z-plane, and we've got the x-plane, or the z-axis and the x-axis makes the xz-axis. And if we're looking at this, if this is positive z, which is this axis here, and sorry, if this is positive x, which is this axis here, and this is positive z, which is this axis here, we see that current is flowing that direction, which means in this diagram it's flowing into the screen, right? And hopefully you've seen this vector notation where an x means the vector is pointing into and a dot means the vector is pointing out. So for point 1, what we're interested in is measuring the amplitude at 40 centimeters in the pure x-axis right here. And so there's going to be a magnetic field that's established like so. And if we were to use the right-hand rule here, pointing our thumb into the page and curling our fingers, we would see that the magnetic field component points down right there, and that is A hat phi. So by inspection from 1, what you can see is that the A hat phi is going to have to equal, it points in the minus z direction. And we can just see that by application of the right-hand rule. So it's a very simple analysis in this situation. So let's do the same analysis for point P2, which was at 0, 0, 40. So that, again, we're looking at the xz plane. And again, the current's pointing in. This time we're looking at 40 centimeters in this direction. So we've got some sort of magnetic field that's circular there. If we point our thumb into the screen and we curl our fingers in around the conductor, we see that the tangent point here points in the positive x-axis. So for point 2, by inspection, A hat phi is equal to plus A hat x. So again, a relatively simple case to analyze. But now let's go to point 3. We've got the same plane as we've analyzed in the last 2 cases, the x-plane and the z-plane, and we've got current flowing into the screen in this case. But now what we want to do is we don't want to come out 40 centimeters. We only want to come out 28.284 in both directions here. So this is 28.284 28.284. Sorry, 28.284. And this is 28.284. And so we need to come at the intersection of those 2 points. If we were to draw that circle, again, I apologize for my terrible artistic talent, but if we were to draw that circle, A hat phi, by the application of the right-hand rule, is going to kind of point in that direction right here. And I've taken my thumb, I've pointed it into the screen, I've wrapped my fingers around the conductor in this direction, and I find that the tangent point, A hat phi, right here, is kind of pointing down and to the right. So I would say by inspection, A hat phi is equal to, well, I have no idea. I can't figure that out by inspection like I did in the last two examples. So there's got to be some sort of numerical way to figure this out. And if you remember from the definition of the Biot-Savart Law, what we used to determine directionality of the magnetic field was the vector cross product. So the direction of A hat phi is determined by the cross product of the vector that points from the current element to the point in space that we measure the magnetic field at, and the unit vector pointing in the direction of the current. So what I need to do is take the cross product of those two vectors. First, the unit current vector, and then the vector pointing from the current element to the point in space. So let's do that for those three cases. We'll do an application up here. If I were to do the cross product, you remember A hat phi is equal to minus A hat z in this case. So if we, by inspection, we see that the current element is pointing in the plus y axis. So AR, which is the direction that the current is flowing in, is equal to, sorry, AC, which is the current the direction is flowing in, is just equal to A hat y. And the vector, the unit vector pointing from the current element to the point in space that we want to measure is A hat r, and that is just pointing purely in the x direction. So the direction of this is going to be determined from the determinant of A hat x, A hat y, A hat z, and then we put the current element first, so 0, 1, 0, and then we put the unit vector for the pointing from the current element to the point in space next, so that's 1, 0, 0. And you guys have done determinants enough now that you can do this math yourself, but it's minus A hat z is the result, which is the same result we got here. Okay, so how would we apply it to point 2? Well, A hat phi is going to be the determinant of A hat x, A hat y, A hat z. The current element doesn't change. It's still flowing in the positive x direction, so that's 0 units in the x direction, sorry, positive y direction. So that's 0 units in the x direction, 1 unit in the y direction, 0 units in the z direction. And what about our unit vector from the current line to the point in space that we're measuring? Well, in this case, it's the unit vector is pointing in this direction. So that's 0, 0, 1, because it's pointing in the z direction. And so if we do this determinant, we get A hat x, which is the same answer we got before. So now let's apply that to a situation where the math is a little more difficult. In this case, we see that A hat phi, it's going to be equal to, again, the cross product of the unit vector pointing in the direction of current flow with the unit vector pointing in the same direction, or the unit vector pointing from the current element to the point in space where we're measuring magnetic field, and we've been calling that A hat r in this application. So the first step here is, well, what is A hat r? To do that, I have to determine what this vector, the r vector is, and then I can determine the unit vector pointing in the r direction. So the r vector is just going to be 28.784 minus 0 pointing in the x direction, plus no component in the y direction, plus, sorry, that's not 7, that's 28, those are 2's, 284, plus 28.284 minus 0 in the y direction, or in the z direction. And so r therefore is equal to 28.284 a hat x plus 28.284 a hat z. Magnitude of r is going to be the square root of 28.284 squared plus 28.284 squared, and that's 40 centimeters there. And so a hat r is 28.284 over 40, pointing in the x direction, plus 28.284 over 40, pointing in the z direction, which is 0.7071 a hat x plus 0.7071 a hat z. So now I can take the cross product, the vector cross product, and that is just a hat phi is going to be equal to the determinant of a hat x, a hat y, a hat z, current still flowing purely in the y direction, and then we've got 0.7071, 0.7071. And the result of this is 0.7071 a hat x minus 0.7071 a hat z. So I can use that to determine total magnetic field strength, and that's just going to be the magnitude, 31.83 amps per meter, times the direction here, 0.7071 a hat x minus 0.7071 a hat z, and that gives me a value of 22.51 a hat x minus 22.51 a hat z. So if we take that result and we come and we just move it up here, so what we see is that for us, we saw that the magnetic field strength at this point is going to there's going to be some magnitude to it, and it's going to have a component that points in the negative z and the positive x. That's what we got by inspection, but that's as far as we could get. Mathematical application using the determinant method of the Biot-Savart law got us that the resulting magnetic field vector is going to be 22.51 in the x direction. It's going to be 22.51 in the minus z direction. And so if we were to add those two vectors together, the resultant vector indeed just lies right there. So the results of the Biot-Savart law jive with what we determined using the right-hand rule. So that's application of Biot-Savart law to magnetic fields. The only other thing that I would like to point out is that in this case we analyzed one current. Much like electrostatics, where there's the concept of superposition, where multiple electric charges can be summed together, the same can be said for magnetic field lines. So if I had another current flowing here and I wanted to determine the magnetic field strength in the middle of them, I would just add the magnetic field components of the two current carrying elements. So superposition not only applies for electrostatics but also for magnetostatics.